Welcome to the 1974 Nobel Prize in Physics. This one went to Sir Martin Ryle and Anthony Hewish. Now, they did a lot of really pioneering work in radio astrophysics, and Ryle was included in this prize because of his observations and really his inventions of a particular apparatus that's still used today and used today in a much bigger way than he ever used it, but it's still very much a tool that we use in astrophysics today. And Hewish for his discovery of this little thing called pulsars, which you might have heard of. Now, lots of weird words here. So we're going to try to take these things one step at a time and really understand what these things are rather than just use the word pulsar. Yay, we're all happy. No, let's explain what a pulsar is. But we'll get to that in a second. Now, pulsars are not only just really these interesting objects that are out there in deep space, but they're also used to make observations that help us test things like the theory of relativity, not just special relativity, general relativity, which is a fantastic test bed for us to have something to work in because it's tough to build those in the lab. This gives us a natural way to do it. So let's just dive right in and check these two guys out because they're pretty cool. Now, stars and other astronomical objects emit far more than just visible light. We're not just lucky that we can see invisible and that's wherever the action is. It's not true. They emit in a much wider range. They emit in the IR, the X-ray, all over the place. But in each wavelength range tells us something different and important. So all the way down into radio, which gets into really long wavelength stuff, that tells you something very important. Now, the trouble is when you get into radio, you have this problem with angular resolution. So think of angular resolution like this. How far away can something be and you can still tell the difference between two different objects? If two cars are too close together in the distance, they look like one car. If two people are standing close together, but they're far away, they look like one person or one object. And when you have a better angular resolution, you can differentiate those objects. And that the wavelength of light tells you what kind of angular resolution you can get based on distance. Because the wavelengths of light are very short, we have a very good angular resolution when we look at things that are within our capability to see. Radio doesn't have that same advantage because the wavelengths can be in the centimeters to meters in some cases. And when you get into gravity waves, they're even longer than that. So we have this problem with angular resolution. And to fix that problem, you need a much better collecting area. So our eyes work for visible light because the wavelength range is down in nanometers. Telescopes work for that because, again, we're talking about nanometers. Now, when you get into radio and you've got meters to centimeters, you need a bigger dish. And the bigger you can make it, the more you can differentiate between two different objects in deep space. The trouble is there's an upper limit to that, right? There's only so big you can build a radio antenna and have it matter. So there's a practical limitation. So enter Sir Martin Ryle. What he did was he figured out that if you did the math correctly and you took data from two different telescopes that were some distance apart, what you can do is get an angular resolution that is the same as if you had a radio dish, the size of how far those two are apart, and they could be on different parts of the planet. You can have one the size of the United States, just with two different receiving antennas on both coasts. Which is a pretty cool thing that he figured out for us. And that's now, in labs all over the world. The VLA out in New Mexico and these types of techniques are used all over the place. And it's thanks to him. And without that, we wouldn't have had the tools we needed to really kind of build out what we needed to discover pulsars and some of the other stuff that's now being discovered. So let's dig in and see what pulsars really are, because it's a word people throw around, but I'm not sure it's really all that well known as to what the thing really is. So let's take a look. Now, Anthony Hewish, while working with one of his grad students working on her PhD, Jocelyn Bell, who did not get named on the prize because typically students are not, that's just the way it works, sorry. They discovered a weird radio source as they were looking at different things out in space. And what it was doing was emitting radio pulses with regular intervals. And what they discovered was the first pulsar. So it wasn't discovered by visible light. It wasn't discovered by X-rays. It was discovered thanks to radio astronomers. And a pulsar is now something that we know very well. And what they are is not just things that emit these sort of beacons out in space, like beep, 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 at different frequencies, but they're actually the compact sort of leftovers after a massive star explodes and goes supernova. So what you have in the middle of a pulsar is essentially what's known as a neutron star. And what happens is that neutron star has charged particles kind of coming out of it and a magnetic field. And as it spins, those charged particles are ejected and interact with the magnetic field, and it creates these radio pulses. So when the pole of the pulsar spins past the Earth, we see a radio pulse. It spins again, we see another radio pulse. We spins another radio pulse. Well, how often do these do it? Sometimes hundreds of times a second. There's actually one in the Crab Nebula that I think is 10 times a second. So they're very well known. And they tend to be very characteristic. So every pulsar is a little bit different. Some of them are the same, but you can always find a little bit differences between them. It's going to be based on some characteristics of how fast they spin, how big is a neutron star, how old is it, all kinds of things go into that, what drives its frequency that it pulses with. But it's because of the magnetic field and rotation and charged particles being ejected, which is kind of a cool thing. Now, who cares? What could they be good? What are they used for? Well, because those charged particles are being ejected at relativistic speeds, it gives us a chance to really test relativity. And relativity has stood up to those tests very well. It's also thought that if we ever develop a method of interstellar travel, pulsars can be used as sort of a GPS in space. So how can you figure out where you're at? Well, you figure out where the closest pulsars are. You measure them. Okay, well, I know what that one is. I know what that one is. That makes me about here. So you can kind of figure out your location in much the same fashion you can with GPS. Theoretically, nobody's ever tried it because we don't really do too much in deep space, at least not yet. We're hoping to get there someday, but not yet. Now, gravity wave studies, they're a great way for us to study gravity waves. The first ever extrasolar planet, which was discovered in 1992, was discovered around a pulsar. So these things are not just these interesting little radio beacons out in space that are kind of cool to listen to. They actually do serve as a purpose. So we can actually help test general relativity, maybe understand gravity waves a little better, maybe try to figure out how to get into interstellar space if we understand gravity and much better than we do today. So they're pretty cool. This prize I thought was really neat because it just involved simple radio waves being discovered with dishes, but they had to develop this new tool that allows you to tie those things together and analyze the data and come pop out an answer that's much better resolution than any one scope could do on its own. Which, by the way, there's now actually similar techniques going on with optical telescopes. They're actually tying together optical telescopes to improve the angular resolution a little bit, or they were doing that about 20 years ago. The trouble is you have to know your position on the planet very well relative to your wavelength. So when your wavelength is in centimeters or longer, as it tends to be in radio waves, that's not difficult to do. When your wavelength is in nanometers, as it is with light, that's really difficult to do. So that's a much harder project, but it has been done. This tying together of things to get better angular resolution has really opened up the astrophysical world as much as space telescopes have. And space telescopes are a much better way to go because you have some upper atmospheric limitations from here on planet Earth. But either way, you're still getting some great data. So I hope you've enjoyed this video. We'll see you in the 1975 video. Don't forget to click like and subscribe, and we'll see you soon.